Hello everyone, my name is Wenting, and today I'm going to talk about Helen maliciously secure coopetitive learning for linear models. And this is a joint work from with Raluca, Joey, and Yang from the UC Berkeley RISE lab. So let me first start with a use case, which is a real use case that I think some of you may have seen before, and is also needed by our RISE lab industry collaborators. So here we have a bank who wants to detect fraud using machine learning. However, fraud is kind of difficult to detect by a single bank because criminals try to conceal their illegal activities across many banks. So really the ideal way to compute a model for fraud detection is to jointly compute a model on customer transaction data across many of these banks. However, this currently cannot happen right now because the banks cannot share data with each other because they're in competition with each other and also possibly due to some privacy regulations. So one possible solution to this is to use a trusted third party where the banks actually transfer their data to this trusted third party, and then this third party outputs a model and gives a model back to these banks. However, this is not very ideal because, again, from our conversations with both the banks and the trusted third party, we learned that actually they have some various concerns from both sides. So from the bank side, they think that the trusted third party is rather expensive, and they don't know how trustworthy this third party is really, because we have seen many cases of third parties being breached. And actually, from the trusted third party side, they were also a bit concerned because now that they have all this data, right, sensitive data from the banks, they kind of become a central point of attack. So they are very concerned for liability reasons if they are actually compromised. So now the question we want to ask is how to actually allow these organizations to cooperate in the presence of competition without sharing the data in plain text with each other and without outsourcing to a trusted third party. And we actually named the setting coopetition, which is where the coopetitive learning comes from, which, by the way, is a real word. This is a definition taken from the dictionary, and we felt that along with the pronunciation guide, if you're interested, and we felt like this setting really captures, or this word captures the setting really well because, by definition, means that you have collaboration between business competitors in the hope of mutually beneficial results. And this coopetitive setting corresponds exactly to a really well-known research direction in cryptography called secure multi-party computation. And the goal of secure multi-party computation, or MPC, is to have the parties emulate a trusted third party via cryptography, but then without actually using the trusted third party, right? So the nice guarantee that it provides is that no party should learn any other party's input beyond what is learned from the final result. And this kind of gives you the security guarantees of utilizing an ideal trusted third-party service. Now, our bank has heard about MPC and is very excited to utilize it to compute this fraud detection model. It wants to make sure that its desired security properties are satisfied. So from a bank's perspective, right, what the bank wants is to only trust itself, and it wants to make sure that its data confidentiality should not depend on the correct behavior of other banks, and that its data privacy is actually guaranteed even if all other banks misbehave. And here I kind of want to emphasize that our coopetitive setting is a little bit different from the federated setting that was mentioned earlier, in that we assume that in this setting, the banks also do not want to leak the intermediate global models either. So the desired properties from the previous page roughly translate to the following threat model. Right? So you have the secure computation. You want to have the secure computation done among all these parties, among the banks themselves, for example. And we want to assume that the attacker who can compromise subset of these parties can actually compromise P-1 out of P parties. And we also want to have protection against a malicious attacker, which means that the attacker can actually deviate from the protocol by trying to maybe execute a different functionality or substituting inconsistent inputs into the computation. However, under this threat model, we do allow the parties to input data of their choice, and we also allow the parties to learn the final model because this kind of you want the original functionality of the training process. So with this, if we take a look at some of the prior work in this area, currently, actually, the framework that handles the requirements is a generic framework, MPC framework, like SPEEDS. However, utilizing, by doing training using a more generic MPC framework is kind of challenging because of performance. So we actually implemented stochastic gradient descent, or SGD, which is a commonly used training algorithm for LASSO, which is a simple regularized linear model using SPEEDS. And in the setting of 4 parties, 100,000 samples of party on a data set of 90 features, we actually estimated that would take 3 months to train this model. We couldn't actually run it, and it ran out of memory way before. And so to solve this problem, we designed and built Helen, which is a training system that gives you the strong security guarantee protection against a malicious hacker who can compromise a majority of the parties. And we decided to support a more restricted subset of the machine learning, which are regularized linear models. But then we felt like that still solves a very significant slice of machine learning and statistics problems like cancer research, genomics, and financial applications. And as it turns out, trying to improve performance under such a strong threat model is a pretty difficult problem. So for Helen, we really had to leverage techniques from 3 different areas, machine learning, systems, as well as cryptography for our solution. And actually, we found that with our insights, we're able to reduce the estimated 3 months to under 3 hours of training the same model in Helen. Okay, so now I'm going to quickly go over, giving you an overview of our techniques from these 3 areas. So first, the first problem we faced was the fact that a common training algorithm, like SGD, right, scans the entire data set, and it actually requires, so if you were to put that entire training algorithm inside the MPC, it would require an expensive MPC synchronization for each iteration. So we instead actually use an alternative approach. So we use a different training formulation called ADMM that is crypto-friendly. And in our model, ADMM is able to scan the data once in the beginning to produce a summary of the entire data. And then during training, it will repeatedly use this data. And with this, the number of iterations as well as the MPC synchronization, both are greatly reduced. However, adapting ADMM to secure computation efficiently is actually still a bit tricky, right? So if we look at the way the summary is being computed, we actually face a second problem. Because we're in the malicious setting, right? The attacker who can compromise parties could actually deviate from the protocol. Then we actually need to make sure that the summary creation is also proven correctly, that the parties need to prove that it has been computed correctly. Unfortunately, if we were to put the entire summary calculation inside these cryptographic proofs, then it becomes pretty heavyweight because the proof now has to take in the entire large training data set as the input, and that will scale in the number of samples of party, which could be very, very large, like in the millions. So we instead, So our second insight from the system side is to create a scalable proof generation of these summaries using first singular value decomposition to reduce the input into much, much smaller input sizes, and this can be done locally in plain text each party. And then the zero knowledge proofs that we use will take in the much, much smaller data set, and we prove in our paper that this still provides the same security guarantees as before. And so we made, okay, so finally, if we take a look at the iterative training process that reuses a summary, there's actually a third problem because the original ADMM formulation actually allows for nice decentralized computation. But then when you formulate that inside of your MPC, it centralizes the computation because it requires everyone to participate for the decentralized computation. or each piece of the decentralized computation from before. So in Helen, we actually bring back the decentralization by using a mixed protocol that combines both homomorphic encryption as well as MPC together, so that you can still do local computation, and then for the other parts that require global synchronization, we put that inside of MPC. Okay, so that is an overview of our techniques, and now I'm going to quickly go through Helen's workflow. So the first stage in Helen is the setup, when the parties need to come together and agree to do collaborative training, and also to agree that they will release the result, which is the model, in plain text. And then during this phase, during the setup phase, the parties also need to do a one-time initialization step to generate some parameters that Helen will utilize during the actual training. And in this case, we are creating a threshold homomorphic encryption scheme that allows, that gives us the strong security guarantees that we have. Since this is done once, if you, at the beginning, if the party, and it can be reused if the party configuration does not change, what we do is we simply put the key generation instead of MPC, and the key generation will give a public key to each party and actually split the secret key into shares so that each party has a single share. And the property this encryption scheme has is that all parties can encrypt, but then you need all P parties together to decrypt the ciphertext. So now it becomes the input preparation phase, which, as you remember, we have to create a summary at the beginning. And this is that step. So during this step, the parties locally pre-compute and prove that these summaries are computed correctly using our insights to, first of all, reduce the input training data into a much smaller summary, and then generate a proof that it's been done correctly. And each party does this separately in a decentralized way. After this step, we go into the iterative training process. And in this iteration, in each iteration, rather, there are two steps. The first step is a local optimization step, where the parties actually compute and prove some local computation in a decentralized way using the summaries that they pre-computed in the input preparation phase, as well as the global weight that they received from the previous iteration, or the initialized weights if you're in the first iteration. So in this case, what they do is simply they use homomorphic encryption to operate on their summary, which is in plain text, as well as the global weight, which is encrypted, and then each party does this in a decentralized way. And next, during the next phase for each iteration is the coordination step, where the parties coordinate together to compute a global weight from their local weights, and this is done just or we're using MPC for this step. And at the end of this step, the global weight, which is computed, is distributed back to all of the parties, and then the parties can start the iterative training process again. So once all the iterations are complete, the parties then use their secret key shares to jointly decrypt the final weights, and the final weights are given back to all the parties in plain text. Okay, great. Now I'm going to go into our evaluation. So in terms of the experiment setup, we used 4 parties. We experiment on EC2, and we put 2 parties in Oregon and 2 parties in Northern Virginia to kind of simulate this more wide area network setting. The baseline that we compare to is SGD, implemented in SPEES, a generic maliciously secure MPC platform. And we make some training assumptions in that SGD has to scan the data, the input data, once. And for ADMM, because we're able to, as I mentioned before, right, one of the insights is that we can actually summarize the data at the beginning and then iteratively train on that, we actually experimentally found the maximum number of iterations it would take for our data sets to converge, which is 10 in this case. I'm not going to show accuracy results here, but you can take a look at that in our paper. But Helen is able to achieve the same accuracy as the baseline model. Okay, so I'm only going to show evaluation on one data set. We do have more in the paper. And this data set is a song prediction data set from UCI, which is a machine learning or a repository for open source machine learning data sets. And for this one, it has, for this particular data set, it has 90 features. And so here's a graph. On the x-axis, we scale up the number of samples per party. And on the y-axis, we have the time in seconds, which is a little bit hard to read. So these are more human readable units on the right side. And so this is the estimated baseline, which is in blue. And as you can see, it scales linearly because, as I mentioned before, SGD has to scan more data as you increase the number of samples per party. Helen, on the other hand, looks constant, but actually does scale up pretty slowly. The reason it looks constant is that the cryptographic operation greatly dominates the plaintext operation in this case. And while the plaintext operation scales in the number of samples, it is very, very fast. So, and the crypto we designed in such a way so that it doesn't scale in the number of samples, which means that you see this near kind of constant behavior. And for 100,000 samples, which is a pretty moderate size, we see a roughly 900x performance gain. Okay, so in conclusion, Helen is a maliciously secure coopetitive training system for linear models. And we're in general very excited about this direction because we think that enabling data sharing can create a lot of value. And yeah, that's it. Thank you.
So thanks. Questions? So maybe I start with one first question. So you basically work with linear models, and I was wondering whether you can extend your approach to also support nonlinear, let's say functions, maybe not models? Or?
Yeah. So I think some of our techniques can definitely be extended to more complex models. I'm actually looking into extending into logistic regression, for example, logistic regression training, because yeah, so basically the local computation part can be translated into that kind of model as well. For neural networks, I would say it's a bit more challenging, okay. But yeah.
I had something different in mind, so maybe you know random kitchen things? Is this a technique from 10 years ago where you can basically take a linear model and then apply some modifications to the features? And you get a little bit of the power of nonlinear classifiers. And my feeling is this would be a perfect fit for your model.
Yeah, sure. I think that would be done in the featureization step, if anything, right? So yeah, I think that approach is definitely complementary to our setting as well. So,
other questions? Okay, so then let's thank the speaker again.
Thank you.